let's talk about a special case of two mutually exclusive events. Okay, so we're going to focus on an arbitrary event A. The complement of an event A is the event of that contains all the outcomes not in A. It's the event where A does not happen. And we write this as A with a little c like an exponent. That's A complement. Okay, so just a brief example to understand what's going on here. Say we're rolling a die. The sample space is 1, 2, 3, 4, 5, 6. Okay? If you're rolling a standard six-sided die, that's what you can roll. That's the sample space. Those are the possible outcomes. Let's let event M be the event of numbers bigger than 4. We roll a number bigger than 4. So that means we could either roll a 5 or a 6. Then M complement is the set of all outcomes that are not in event M. So what's not in event M? Well, that'd be 1, 2, 3, and 4. Okay? Graphically, what's going on here is if we have an event A here, if this is event A, then everything outside of that, everything that's not in A is A complement. So A complement lives over here. Okay, that's A complement. So notice that together they fill the whole sample space. Okay, so what are some properties of these complementary events? Well, we've already talked about a couple of them. First of all, they're mutually exclusive. A and A complement, two complementary events, are mutually exclusive. But there's more. They fill the whole sample space, right? Every possible outcome is an A or A complement. Okay, so what does that mean? Let's look at the addition rule and see what that's telling us. Okay, that means that the probability that A or A complement happens, because the events are mutually exclusive, we could use the simplified addition rule. That is, we could just add the probabilities of the individual events. Okay, but we could do more. We have this other piece of information. They're not just mutually exclusive. They also fill the whole sample space. Every possible outcome is in one of these two events, which means the probability that one of them happens is 100% chance. There's a 100% chance that one of these two things happen. If we go back to our dice example, if M doesn't happen, if we don't roll a 5 or a 6, then we roll a 1, 2, 3, or 4 on our dice. If we don't roll a 1, 2, 3, or 4, then we're rolling a 5 or 6. There's a 100% chance of one of those two things happening. That's always true for complementary events. So instead of just leaving this, we actually know what this probability is. This is 100% or 1. And so for two complementary events, we could say that the addition of their probabilities will always equal 1. This is going to be especially useful if we're looking at something like winning and losing. Okay, for a lot of games, winning and losing are the only two possibilities. Okay, if that's the case, then they're complementary events. If you can only win or lose in a game, then then the event that you win is the complement of winning is losing. Okay, if you do not win, you lose, and if you do not lose, you win. Complement of losing is winning. The complement of winning is losing. Again, we're assuming there's only two possibilities here: you win or you lose. Okay, there are games, of course, where there is another option. For example, if you play tic-tac-toe, it's possible that you don't win and you don't lose. It could be a draw. Or if you play rock, paper, scissors, maybe you both pick paper, it's a draw. Neither win or lose. That's not what we're assuming here. We're assuming that you either win or lose. There is no third option. Okay? That means these two events would be complementary and therefore mutually exclusive. And therefore, using our previous formula, if we take the probability that we win plus the probability that we lose, because those are the only two options, and one of those two things has to happen, there's a 100% chance of one of those two things happening.